Hello, I'd like to share with you about Sophie Germain, a French mathematician who lived between 1776 and 1831. As a young woman in France at that time, she was barred from studying mathematics in the universities. Her family discouraged her love of mathematics. However, in the evenings, when the household was asleep, she would wake up and sneak into her father's library with her candle and read his books on mathematics, and she self-taught herself to a high level. As she entered young adulthood, she would correspond with the leading mathematicians in Europe at that time, signing her name as Monsieur Leblanc to avoid being discovered as really being a woman. For at that time, if they'd known her to be a woman, they would have not corresponded with her. Over the years, as these correspondence grew, she did reveal her true identity, and mathematicians as illustrious as Gauss continued to correspond with her and respected her as a fellow mathematician. Her studies today are particularly important as she did pioneering work in the areas of number theory, in particular a great love for prime numbers. So let's have a little look at some of the things that Sophie worked on. So firstly, prime numbers. What is a prime number? So prime numbers can either be prime or they can be composite. So a prime number is a number that is only divisible by itself or 1, whereas a composite number can be made up by multiplying two other numbers together. So let's consider 12. 12 can be made up with 2 and 6, or 3 times 4. Let's think about the number 7. 7 can only be a multiple of 1 or 7, so itself or 1. Therefore, 7 is a prime number. 1 is a prime number. 2 is a prime number. 3, 5, and 7, and so on. These are all prime numbers. And if it's not a prime number, it's a composite number. Interestingly, all composite numbers can be written as a series of multiples of prime numbers, and we call this prime factorization. So let's consider the number 24. It's not prime, and we can create what's called a prime factor tree. So let's pick two numbers that multiply together to give us 24, with one of them being prime. So if it's an even number, the obvious way to start is by taking 2, and then 2 times 12 is 24. This is prime. We can't take this down to any smaller number. 12 can be written as 2 times 6. 6 can be written as 2 times 3. Now we've got all these prime numbers. So this shows that 24 can be written as 2 times 2 times 2 times 3, or 2 cubed, there's 1, 2, 3, 2 cubed times 3 will give us 24. Now, the reason primes are so important now is in the area of cryptography. We want to be able to encrypt personal data to send it over the internet, for example, in internet banking. And one of the ways that we do, the way that we do cryptography now is to encrypt data using very big prime numbers. We can see here the first prime numbers 1, 2, 3, 5, 7. There's quite a few of them between 0 and 10, but as you get to larger and larger primes, larger and larger numbers, it's harder and harder to find these prime numbers, which makes them very useful for cryptographers. Now, what Sophie Germain discovered, she discovered a family of primes which are now known as Germain primes. She discovered that if you take some prime number, which we will call P, and you multiply it by 2, and then you add 1, and that gives a new prime number, then this prime number is a Germain prime. Let's see an example. Let's take 3. So P is going to equal 3. So 3 times 2 equals 6. 6 add 1 equals 7. 7 is a prime number, so 3 is a Germain prime. Let's try 7. See, we've got 7 here. 7 times 2 is 14. 14 add 1 is 15. 15 is not prime, it's a composite number. Therefore, 7 is not a Germain prime. And it's these Germain primes that are particularly useful in modern cryptography, where cryptographers will look for very, very large Germain primes and use them in the encryption of our personal data, which makes internet banking and the transfer of secure, sensitive data over the internet possible. Let's look at another area in which Sophie Germain worked. So many people you'll be familiar with Pythagoras, this Greek philosopher who did work on right-angled triangles. So here's our right-angled triangle with sides A, B, and C. And Pythagoras' theorem states that C squared equals A squared plus B squared. Now in the 1600s, there was another French mathematician called Fermat. And Fermat wrote lots of little theories and ideas in the margins of books. And he was a genius in mathematics and made many discoveries. But many of the times when he wrote these things down in his books, he wouldn't give a proof. So in one of his journals, in one of his books, there's this little scribble that he wrote stating that if for Pythagoras' theorem to work, it only works if you take the square of these sides. It doesn't work if you cube them, it doesn't work if you raise them to the power 4. So C squared equals A squared, take those away. C to the power n equals A to the power n plus B to the power n is only true if n equals 2. It cannot equal any other number, and this is called Fermat's last theorem. And the reason it's his last theorem is because after Fermat died, mathematicians took his journals, took his books, and went through all these. There was many other little theorems that he'd scribbled in his margins of his books, and they went through them systematically, and they proved them, all except this one. Now, to be a mathematical proof, you need to prove it for every single value of n. And because n can take any number, there's an infinite number of possibilities. Even if you took the biggest supercomputer, it's never going to go through all the numbers because there's an infinite number of possibilities. So for the centuries after Fermat died, mathematicians were trying to work this out. They didn't find any number that where it disproved that his theorem was true, but they couldn't do a rock-solid proof. Sophie Germain, in her work on primes, she managed to prove that this holds in a mathematical sense of a proof for primes less than 197, which doesn't sound like a big deal because you could work through them all, but because she wasn't working through each number between 1 and 197, she actually gave a mathematical proof for this to be true. It was a step forward, and it was a step into modern number theory. And from this work, that this was like the gate into this problem for other mathematicians to come after her. Fermat's last theorem was finally proven to be correct in 1993. So it was quite a difficult one for mathematicians to solve. Now, Sophie Germain, as she grew in, as many of the male mathematicians began to respect her for the mathematical genius that she was able to enter a competition that was quite illustrious in its day with the Paris Academy of Sciences. Even though she wasn't allowed to get a degree, she was allowed to enter this competition. And what they were doing is work on these. Now, these are known as Chladni figures. So you may have seen sometime on YouTube or whatever, a metal plate and sand sprinkled all over it. And then it maybe with a violin bow or a speaker of some kind. Let's just draw a speaker down here. And it plays sound waves at certain frequencies, and if you get this frequency right, you get these patterns. And it's all to do with the resonant frequency of the plate and the different nodes of vibration that can be produced. Now, this is the idea of this isn't a two-dimensional plate. It's the same idea if you had a skipping rope and two people holding the skipping rope, and they were if you were to wave the skipping rope up and down, and so you can get it so it makes this kind of pattern. Now, if you were to shake the skipping rope, so you shake the skipping rope up and down like this, and so it's just like this kind of shape that it makes. If you were to shake the skipping rope more vigorously, you might create a pattern like this. So it's going up and down, but it looks like you've got this point in the middle that's always stationary. And what you've created here is a standing wave. And what's happening in these is a similar idea, but this is in 2 dimensions. And you can make these beautiful patterns. So this competition was to look at the mathematics behind these. And it was a fiendishly difficult problem. When the competition was opened, everybody basically dropped out, apart from Sophie Germain, and she worked on this problem. She submitted her solutions, and on her 3rd attempt, she won the prize for this, which was an amazing achievement for a woman who had self-taught herself with a candle in her father's library, and wasn't allowed to access the best universities in Europe like her male contemporaries. So I hope you enjoyed this little video just explaining a little bit of the history of mathematics and one of the unsung heroes of mathematics. If you look at the names of the people who she was working with, like Carl Friedrich Gauss and Poisson, who are big names in mathematics even today, and if you go to university, you'll hear their names prop up. Sophie Germain is quite unknown in the wider community, which is a bit of a shame given the things that she achieved against the odds. So thank you for listening.